To start this story, let's go back to the analog days. Wireless microphones seem simple on the surface. Audio goes in, audio comes out, no cable required. But getting audio from a transmitter to a receiver reliably is genuinely tricky. Here's how it works. When you send audio wirelessly, you're encoding it onto a radio signal, specifically a frequency modulated, or FM signal. The same basic concept as FM radio. The problem is that FM signals support a limited dynamic range. When a singer's voice goes from a whisper to a belt, an analog FM system might struggle to handle that full range cleanly on its own. So engineers designed a so-called compander in the system that compresses the audio signal that goes into the transmitter, reducing the dynamic range down to something the FM signal can carry, and then expanding it back out at the receiver. Compression on one side, expansion on the other. A compander. For a long time, it worked well enough, but companders left artifacts in audio passing through them. The compression and expansion process introduced subtle coloration to the sound, a kind of pumping or breathing that you might notice on loud transients or in the tails of a long note. An experienced engineer could often hear the difference between a wired mic and a wireless one. Not always and not dramatically, but it was there. But for a lot of users, that was an acceptable trade-off. The freedom of going wireless was worth the slight audio quality cost. But when digital wireless systems started arriving in the professional market, the compander was no longer necessary. Digital wireless audio doesn't need it. When you transmit audio as digital data, a stream of binary information, you're not fighting the dynamic range limitations of an FM signal in the same way as you are with analog. And that means the audio that comes out of the receiver is going to be far closer to what went into the transmitter. Shure launched their ULX-D line in January 2012, and that was a big milestone. It was the first digital wireless system in Shure's lineup to truly match the performance standard that their professional analog systems had set. Flat 20 Hz to 20 kHz frequency response, more than 120 dB of dynamic range, and no companding artifacts. But really, the audio improvement wasn't even the most important part of going digital. The hidden bonus was spectrum efficiency. With an analog FM signal, the frequency deviation, how much the signal wanders around the center frequency, varies based on an analog audio signal. That unpredictability means you need to give each channel enough extra breathing room on either side of the center frequency to avoid interfering with neighboring channels. In digital wireless, though, the deviation is more predictable and contained. That means you can pack channels closer together. Practically speaking, digital wireless systems can fit roughly twice as many simultaneous channels into the same slice of spectrum as their analog counterparts.